Okay, so a superposition state is basically a function which is a linear superposition of the different eigenstates, the different eigenfunctions, the psi sub n's. Okay, so f of x, the function, is equal to, and sometimes we just call this psi of x without a subscript, is equal to a linear superposition of the eigenfunction psi sub n's with these coefficients which in front of each one, which is just a multiplier, sort of an amplitude coefficient. Okay, so if you sum this series from n equals 1 to infinity, then you can make any arbitrary function of f, again, that satisfies the boundary conditions by basically adjusting the amplitude coefficients c sub n appropriately. So since we know that our eigenfunctions are root 2 over L sine n pi x over L, this is just how you write it explicitly. And those of you who might have taken a linear algebra class or complex analysis class may recognize that that this is the Fourier series for an arbitrary function with the periodicity L and whose value f at 0 at x equals 0 is equal to 0. Okay. All right. So you have some arbitrary function of x which satisfies the boundary conditions. Okay, and that means that you can put the particle, which is the wave which is representing the particle, the wave function which is representing the particle, can take on. You can somehow prepare a state which is a particular superposition which gives you a this function. Now, if you know the function, you may want to know what these coefficients are actually. So you can think of this two ways. You can think of, I want to build a function, an arbitrary function, from these eigenfunctions, from these eigenstates, or you might say, well, I actually have an arbitrary function that I know and that satisfies the boundary conditions, and then what I want to do is decompose it. That is what I want to know these coefficients c sub n. Okay, and so the way that you find the coefficient c sub n for a particular arbitrary function f of x is that you project the function onto the desired basis state, meaning that you and this is how we do projections in this context. We, just like you project a vector, an arbitrary vector going off in a particular direction, you can project that onto particular direction, orthogonal. If you have an orthogonal set of axes, you can project that arbitrary vector onto a particular one of the axes, basically by taking the dot product, and this is so the inner product. This is essentially the inner product for these wave functions. So you have this arbitrary function f of x. It's a wave function. It's a superposition state wave function. You multiply it by the complex conjugate of the basis state that you want to find the coefficient for. Okay, so you want to find the coefficient c sub m. So you multiply your arbitrary function by the complex conjugate of that basis state psi sub m. You integrate this from minus infinity to infinity. Okay, and if you do that, then if we write this out explicitly, again, f of x is just this arbitrary superposition, okay, of the basis states. So it's the sum from n equals 1 to infinity of these coefficients c sub n times psi sub n. Okay, so I've just brought these outside the integral because they don't depend on x, and now again we're multiplying that by the complex conjugate of the mth basis state, okay, psi sub m star. And what we know then, as we've seen before, is that this product here, when integrated over all space, is, so this goes from 0 to L now for the square well, gives us the Kronecker delta function, okay, and then that multiplies the Cn, and so this Kronecker delta function is only non-zero. It's equal to 1 when m equals n, and so the only term in this sum which contributes is the mth one, and so we get c sub m. Okay, and so that's how you find the coefficient c sub m, is that you basically project the function onto the corresponding eigenstate or eigenfunction.